Glacial sediments grease the gears of plate tectonics. Earth's outer layer is composed of giant plates that grind together, sliding past or dipping beneath one another, giving rise to earthquakes and volcanoes. These plates also separate at undersea mountain ridges, where molten rock spreads from the centers of ocean basins. But this was not always the case. Early in Earth's history, the planet was covered by a single shell dotted with volcanoes, much like the surface of Venus today. As Earth cooled, this shell began to fold and crack, eventually creating Earth's system of plate tectonics. According to new research, the transition to plate tectonics started with the help of lubricating sediments, scraped by glaciers from the slopes of Earth's first continents. As these sediments collected along the world's young coastlines, they helped to accelerate the motion of newly formed subduction faults, where a thinner oceanic plate dips beneath a thicker continental plate. The new study, published June 6, 2019 in the journal Nature, is the first to suggest a role for sediments in the emergence and evolution of global plate tectonics. Michael Brown, a professor of geology at the University of Maryland, co-authored the research paper with Stefan Sobolev, a professor of geodynamics at the GFC German Research Center for Geosciences in Potsdam. The findings suggest that sediment lubrication controls the rate at which Earth's crust grinds and churns. Sobolev and Brown found is largely the same at the continental scale, in the ocean trenches where tectonic plates meet. The same dynamic exists when drilling Earth's crust. You have to use mud, a very fine clay mixed with water or oil, because water or oil alone won't work as well, Brown said. The mud particles help reduce friction on the drill bit. Our results suggest that tectonic plates also need this type of lubrication to keep moving. Previous research on the western coast of South America was the first to identify a relationship between sediment lubrication and friction along a subduction fault. Off the coast of northern Chile, a relative lack of sediment in the fault trench creates high friction as the oceanic Nazca plate dips beneath the continental South America plate. This friction helped to push the highest peaks of the central Andes Mountains skyward as the continental plate squashed and deformed. In contrast, further south there is a higher sediment load in the trench, resulting in less friction. This caused less deformation of the continental plate and, consequently, created smaller mountain peaks. But these findings were limited to one geographic area. For their study, Sobolev and Brown used a geodynamic model of plate tectonics to simulate the effect of sediment lubrication on the rate of subduction. To verify their hypothesis, they checked for correlations between known periods of widespread glaciation and previously published data that indicate the presence of continental sediment in the oceans and trenches. For this step, Sobolev and Brown relied on two primary lines of evidence: the chemical signature of the influence of continental sediments on the chemistry of the oceans and indicators of sediment contamination in subduction-related volcanoes, much like those that make up today's Ring of Fire around the Pacific Ocean. According to Sobolev and Brown's analysis, plate tectonics likely emerged on Earth between 3 and 2.5 billion years ago, around the time when Earth's first continents began to form. This time frame also coincides with the planet's first continental glaciation. A major boost in plate tectonics then occurred between 2.2 to 1.8 billion years ago, following another global ice age that scrubbed massive amounts of sediments into the fault trenches at the edges of the continents. The next billion years, from 1.75 billion to 750 million years ago, saw a global reduction in the rate of plate tectonics. This stage of Earth's history was so sedate, comparatively speaking, that it earned the nickname, the boring billion, among geologists. Later, following the global snowball Earth glaciation that ended roughly 635 million years ago, the largest surface erosion event in Earth's history may have scrubbed more than a vertical mile of thickness from the surface of the continents. According to Sobolev and Brown, when these sediments reached the oceans, they kick-started the modern phase of active plate tectonics. Aftershocks of 1959 earthquake rocked Yellowstone in 2017-18 on August 17, 1959. Back when Dwight D. Eisenhower was president, the U.S. had yet to send a human to space and the nation's flag sported 49 stars. Yellowstone National Park shook violently for about 30 seconds. The shock was strong enough to drop the ground a full 20 feet in some places. It toppled the dining room fireplace in the Old Faithful Inn. Groundwater swelled up and down in wells as far away as Hawaii. 28 people died. It went down in Yellowstone history as the Hebgen Lake earthquake, with a magnitude of 7.2. And in 2017, nearly 60 years and 11 presidents later, the Hebgen Lake quake shook Yellowstone again. A swarm of more than 3,000 small earthquakes in the Maple Creek area in Yellowstone National Park but outside of the Yellowstone volcano caldera between June 2017 and March 2018 are, at least in part, aftershocks of the 1959 quake. That's according to a study published in Geophysical Research Letters by University of Utah geoscientists led by Guaning Pang and Keith Koper. These kinds of earthquakes in Yellowstone are very common, says Koper, director of the University of Utah Seismograph Stations. These swarms happen very frequently. This one was a little bit longer and had more events than normal. We don't think it will increase the risk of an eruption, Pang adds. A long seismic tail. Taken together, the more than 3,000 small quakes of the Maple Creek swarm can be divided into two clusters. The northern cluster consists of Hebgen Lake aftershocks. The quakes fell along the same fault line, and were oriented the same way as the Hebgen Lake event. Also, the team didn't see signs that the northern cluster was caused by movement of magma and other fluids beneath the ground. Koper and Pang says it's not unheard of for aftershocks of a large earthquake to continue decades after the initial event. Pang, for example, has also studied aftershocks as recent as 2017 from the 1983 Bora Peak earthquake in central Idaho. There are formulas to predict how many aftershocks you should see, Koper says. For Hebgen Lake, there looked like a deficit in the number of aftershocks. Now that we've had these, it has evened things out back up to the original expectations. A second culprit. The southern cluster of the Maple Creek swarm seems to have a different origin. Although the northern cluster was lined up with the Hebgen Lake fault, the southern cluster's lineup was rotated about 30 degrees and the quakes were about 0.6 miles, 1 kilometer, shallower than the northern cluster. So, the researchers concluded, although the shaking in the northern cluster influenced the southern cluster, the primarily cause of the southern shaking was likely subsurface movement of magma. We do consider it to be one swarm altogether, Koper says. Because they were so close, there was some feedback and influence between the two sections. Koper says that the results highlight how earthquakes are different than other natural hazards. Floods, hurricanes or wildfires are over when they're over. Earthquakes don't happen as a single discrete event in time, he says. The specter of aftershocks can continue for months, years or even, as Maple Creek shows, decades. The study was funded by the United States Geological Survey, the Brinson Foundation and the Carico Funds.